But as you observe it, I envision a sensation beginning to take over you. There's something disconcerting about it, because you may have observed that what is truly occurring is that the egg is detaching from itself. Now, you will notice the yolk and white separate, and now they are being poured back into the egg. We all sense, deep down, that the universe doesn't operate this way. A scrambled egg is a haphazard blend, like porridge. While it may be a delectable porridge, it's still not uniform. The egg is a magnificent and intricate entity. It can lead to even more complicated things, like a chicken, for instance. And we intuitively understand that the universe doesn't transition from randomness to intricacy. In fact, this essential truth is reflected in one of the most basic principles of physics, the second law of thermodynamics, or the law of entropy. This principle essentially states that the general trajectory of the universe is from order and organization to chaos and the absence of order, and indeed to porridge, a lack of uniformity. And so that video feels somewhat peculiar. Yet look around us. What we witness around us is extraordinary complexity. Eric Bainhocker estimates that just in New York City, approximately 10 billion stock units, WTM, are exchanged, representing various goods. This figure is hundreds of times the number of creatures on the Earth's surface, and these exchanges are conducted by beings whose population is 7 billion people, connected through commerce, travel, and the internet into a globally interconnected system of incredible intricacy. So here's the major riddle. In a universe ruled by the second law of thermodynamics, how can this sort of complexity, which I described, the type of complexity present in you and me, and in the conference room, come into existence? Well, the answer seems to be the universe can generate complexity, but with considerable difficulty, in certain pockets/regions, what my colleague Fred Spire refers to as moderate conditions emerge. Not too hot, not too cold, but just right to permit complexity to develop. And as a result, more intricate things start to appear. And where you have more complexity, you can generate even more complexity. Thus, complexity is built step by step. Each stage is magical in its own way, because it gives the impression of something entirely new, emerging almost from nothing vacuum in the universe. In the grand timeline, we call these moments time thresholds, and at each time threshold, the processes become progressively more intricate. Complicated things become more fragile, more vulnerable to influences, and favorable conditions move toward tension, making it harder to generate complexity. Well, as highly intricate beings, we have a great need to understand the story. That explains how the universe can create complexity, despite the second law of thermodynamics, and why complexity implies fragility and vulnerability. And this is the tale we recount in the great history. But to do so, we must do something that may initially seem utterly impossible. We must take a comprehensive look at the entire history of the universe. So let's begin. Laughter. And let's start by rewinding the history 13.7 billion years to the beginning of time. Around us, there's nothing, not even time. Imagine the darkest, most empty thing, and then shape it into cubes in an endless, countless sequence. And here we are now. Then suddenly, a lightning bolt/explosion. A whole universe materializes, and we pass the first threshold. The universe is minuscule, smaller than an atom. Its temperature is beyond comprehension, and it contains everything that exists in the current universe. So we can envision it exploding and expanding at a phenomenal speed. At first, it's just mist, but soon, distinct things start to materialize from that mist. In the first second, energy disperses into distinct forces, including electromagnetism and gravity. And energy does something else, something remarkable. It solidifies to form matter, quarks that create protons, and leptons containing electrons. And all of this happens in the first second. Now, let's move forward 380,000 years. That's twice the span of human existence on this planet. And now, simple atoms of hydrogen and helium come into being. Now, I'd like to pause for a moment, 380,000 years after the universe began, because we actually know a lot about the universe at this stage. And above all, we know that it was exceedingly simple. It consisted of vast clouds of hydrogen and helium atoms with no structure. It was a cosmic porridge. But that's not entirely accurate. Recent studies by satellites like the Wilkinson probe with varied waves have revealed that there are indeed slight variations in this background. What you see here, the blue areas have a temperature about 1,000th of a degree lower than the red regions. They are slight variations, but they were sufficient for the universe to move forward to the next stage of complexity building. Here's how things unfold. Gravitational forces are strongest where there is more matter. So, in areas where the density was slightly higher, gravity begins to gather clouds of hydrogen and helium atoms. We can imagine the early universe splitting into billions of clouds. The clouds start to condense one by one. Gravitational forces grow as density increases, and the temperature rises at the center of each cloud, and then at the center of each cloud, once the temperature exceeds 10 million degrees, protons begin to fuse, releasing immense amounts of energy, and then an explosion. We get the first stars. After approximately 200 million years following the Big Bang, the stars begin to appear throughout the universe, billions of them, and the universe is now far more fascinating and much more intricate. The stars will create moderate conditions suitable for surpassing two new thresholds. When massive stars die, they generate such high heat that protons begin to fuse into unusual combinations, creating all the chemical elements in the periodic table. If, like me, you were a gold ring, it was formed in a massive explosion, supernova. The chemical composition of the universe is now more complex, and in a universe with more chemical variety, more things can be created. What begins to happen is that around small suns and small stars, all these elements mix and spiral together, and their motion is accelerated by the energy from the star, forming particles and tiny specks, forming rocks and bodies, and eventually forming planets and moons. Thus, our solar system formed. About 4.5 billion years ago, rocky planets like Earth are much more intricate than stars because they consist of a far broader diversity of materials. So we passed a fourth threshold of complexity. Now the processes continue toward complexity. The next phase introduces entities that increase their fragility and susceptibility to influences, but in return they are more creative and more capable of generating additional complexity.